Okay, guys, so let's get started with the second talk of this session. Now we have Ewelina HANKIEWICZ. Sorry.
Very good.
From Würzburg University, and she's going to be talking about thermal versus electric response of superconducting topological materials.
Thank you very much for this nice introduction, and also thank you, organizer, for inviting me here. And I can see I couldn't actually, I wasn't sure if this is 21st or 22nd May. But anyway, so I will actually try to convince you that at least theoretically, Majoranas might be more widespread than we expected. And obviously, Majoranas are interesting from the point of view of quantum computation. So we are coming back to our topic. On this other hand, I wanted to convince you because Majorana is a neutral particle that you could observe it in the thermal transport. So I will connect to what Francesco was saying, but I will not be using any nonlinear transport here. Okay. So this is first, let me acknowledge my group. So as you can see, we are quite happy drinking beer. So the guys who are very much involved in this research is Benny, who just finished his PhD, Raphael and Daniel. And you will see that actually they did a lot of the work which I'm gonna talk about today. And I am looking for PhD students and postdocs, so if you find what I'm showing here interesting, then please apply. Okay, so I will make a brief intro because we didn't speak so far about topological materials. We just talked about bilayer graphene, we talked about thermal transport, but we didn't really talk about topological materials. And then I actually will try to convince you that the thermal conductance may be a better way to detect Majorana bound states than the electrical one, at least in the 3D topological insulator, which are proximatized by S-wave superconductivity. And finally, I will go to the 2D Luttinger semimetals, so really to the whole system, and shows you that actually it could be much better platform to find Majorana fermions than the platform which is related to the electrons. Good, so just this is a very simple introductory slide, which just shows that in general, if we have a topological material, then something interesting happens. So in the trivial materials, obviously, we have a band gap, and we have some states inside of a gap, which we can remove by perturbation. This is very different for the topological insulator, which has the surface states, which are impossible to remove by simple perturbation. What we need to do is we need to close the gap and reopen it. And this is similar to the situation of let's say, a Mobius strip. So obviously, to make a Mobius strip, we need to extra twist. We need to make an extra twist in the system. So what I will be interested in this talk is mainly 3D topological insulators. So they are insulating in the bulk. At least that's what we would wish for. And they have the surface states where the spin and momentum is coupled, so sigma dot p. So here momentum and spin are coupled. And obviously, one can obviously see them already in many different compounds, bismuthium selenide, bismuthium telluride. But also, if you take mercury telluride and you strain it with the tensile strain, you also obtain 3D topological insulator. So what's interesting here is obviously that you have this, if I put a potential and I wanted to couple the state with P and minus P with opposite momenta, then I cannot do this by the scalar disorder. So in general, the P and minus P are orthogonal, and this gives me lack of the backscattering in these materials. At least at this lack of backscattering or scattering over the 180 degree. Okay. So now just let me say 2 words about the S versus P wave superconductivity, because I will need this for my explanation. I'm guessing tomorrow there will be lots of talks concerning also Kitaev model and these realizations. So, I mean, if I have S wave order parameter, then I usually have a singlet. And this means is that obviously this representation of the spin, while when I have a triplet, then my orbital part is odd and my spin part is even. And the first model which was introduced was Kitaev model, where we actually have additionally to the chemical potential. Oh, this is really bad. We have also kinetic energy and the non-local pairing between the two neighbors, which gives me what is called p-wave pairing. Okay? And in these systems, I can see Majorana fermion, where the particle operator is equal to the antiparticle operator, and it has actually fermionic relations. So there is topological transition, which allows me to go from the chain where I have a trivial phase to the chain where actually there are two Majoranas on the edges of my wire, and these two Majoranas are protected. They are in the, they form double degenerate state, zero energy state. And we are very much interested in finding these particles, as many of you know, because of the topological quantum computation. So these are the particles which are protected by the superconducting gap. And because of this, we could think about exchanging them. Obviously, we cannot do all. We cannot, for example, do CNOT gate on Majoranas itself, but we can do a lot of at least single gate with much less error corrections. Okay, so the question is obviously to see this Majorana in transport and to be able, at least before we do exchange of these Majoranas, to at least be sure that what we see, it is related to the Majorana signal. Okay, so this is actually bringing me to the topic, first topic of this talk. So I wanted actually to show you that this is very difficult to induce Majorana and to see it in the electrical transport. And the reason for this is, at least we know that strontium rutenite oxide is not anymore p-wave superconductors. That's at least what many experimentalists are saying. They're saying that this is more in a direction of d-wave superconductor, or maybe d plus id. But so the question is how to induce the p-wave superconductor, and we use the simplest materials. So what we do here, we take the surface state of topological insulator and we put the superconductor. So this is actually a singlet superconductor. So what happens is we proximatize the surface of the 3D topological superconductors by inducing superconductivity in the surface state. So this is a simple Hamiltonian, which obviously gives me the spin momentum locking in the surface states, which I showed before. I use Bogolyubov-Dejean equation, where I have an electron, quasi-electron, and quasi-Hall excitations, which are then coupled by the superconductor here. And if I look at this, so this is what you can say this was done by Fu and Kane. But the problem with Fu and Kane is that they didn't tell us all truth. So if we have three-dimensional topological insulator, then actually, so you see surface state Hamiltonian. I actually put it induce singlet pairing. Some shift of the spectrum due to tunneling you can have. But if you actually look up, it's different from the Kitaev model, because what happens is that you do not have a node in the superconducting order parameter. And p-wave superconductivity appears actually in the green function of the condensate. So additionally to the singlet, which is this sigma 0, sorry, this is really bad. You have actually the sigma dot p, which is related to the helicity. And this is actually the triplet, which doesn't break time reversal symmetry. So you have S plus minus 1 triplets, and they are in the same amount. And obviously now you have a problem, because you have a mixed order parameter because of the lack of spin rotational symmetry. And it's not so easy to actually see the Majorana in the transport. Okay, so one thing which you can do, which we did some time ago with Grigory Tkachev, is to take a superconducting junction and put here the gate. Yeah, so this is just a very normal material. So this is Josephson junction geometry on the topological surface state. And then by tuning this barrier, you can actually eliminate all modes, only the first two modes, which are related to the Majoranas. So what happens is that if you do not have a magnetic field, then you have time reversal symmetry in a system, and if you have a barrier, then time reversal symmetry, which would change spin to the minus spin and momentum to the minus momentum, doesn't allow you reflection. So the first mode is tunneling with the transmission of one, which is from the relativistic physics, we call it superconducting Klein tunneling, and you can distinguish it from other modes. So what happens when I have a surface of 3D topological insulator? I have many modes, really. So obviously, the first two modes, they are related by time reversal symmetry and by helicity, and they are actually related to the Majorana fermion, especially if I would, here it is helical, it would become chiral if I added strong magnetic field. But now all other modes are actually with gap, and what happens is that they are a trivial Andreev bound state. So now there is a problem of distinguishing in theory and in experiment between these two species. So one thing to do is, because we have to remember, and I think many people forget this, that the Andreev bound states in the superconducting, normal superconducting junction are actually also, if the D would be equal to 1, if the junction is completely transparent, they also have for pi periodicity. So one needs to be very careful, and the only way to actually distinguish the special modes for the STIS junction is to tune and look at the supercurrent as a function of the barrier in the normal regime, or, for example, to look at the current phase characteristic, which gives you some kind of skewness, which is different from the SNS junction. So we tried both of these methods, but it's still quite difficult. So then we actually get to the conclusion, why not to try to use the neutrality of Majorana? And because the Majorana is neutral in general, then I should see it very well in the thermal transport. So that's where we are coming into. So we actually decided to look at the thermal transport through the Josephson junction. So what happens here is that I have actually gradient of the temperature on the two superconductors, and I also change the phase difference. Yeah? And now you can have different processes because of this. So you can have an electron co-tunneling, cross Andreev reflection, so tunneling as a whole, or reflection as an electron, or reflection as a whole. Yeah, but what I am actually interested in here is the thermal conductance. And now you should be very upset with me, because the thermal conductance, how much dissipation do I have through the superconducting gap? 0. Yeah, so I cannot have a transport through the superconducting gap. However, what I can, with this temperature, excite the Cooper pair, and I have then information about the phase difference between the two superconductors. So what I am actually using is quasi-particles above the superconducting gap, as well as broken Cooper pairs because of the temperature. So I am not looking now at the superconductivity or supercurrent or anything like this inside of a gap, because this is obviously the thermal current through the superconducting gap is 0. Yeah? So what I can, however, calculate is still thermal conductance when I split the Cooper pair or go with a quasi-particle. And it's very similar to the electrical conductance, but additionally to the transmission coefficient, I have to integrate over energy and the Fermi distribution in respect to the temperature, obviously. So I can then look what happens. Yeah, and I can see that actually the thermal transport is much more sensitive. So now this is the same calculation as we did before, but actually for the gradient of the temperature, not looking just at the supercurrent, okay? And what we see here is actually this white thing is an Andreev bound state, okay? So this phi is phase, and omega over delta is energy, and we can see the change of the conductance here. So obviously inside of the gap, I have only Andreev bound state, okay? And the Z equal 3 means the large barrier. So this is for the superconducting free DTI superconducting junction, and this is for the superconductor normal superconductor junction. And you can see that obviously with the barrier, this state here becomes close to the band gap, the Andreev state, because it's trivial. And the redistribution of the states above the gap also changes because of the normalization of the density of states. So you see that for the topological insulator, my phase-dependent conductivity as a function of phase always have minimum for phase difference equal pi, while the normal superconducting normal junction, it actually has minimum or maximum depending where the state is. So meaning if it's more behaving as an as it's deeper in the gap, a superconducting gap, or if it's going close to the boundary. Yeah, so actually here we also have many modes. But the funny thing is that there is geometrical factor in the thermal conductivity, which makes all of the states for the phase-dependent thermal conductivity giving me the minimum. And this is nice because we said when it looks like indeed the thermal conductivity is more sensitive to Majorana fermions. And then we contact Francesco Giasotto, and we ask him if he could actually measure something like this and what is the sensitivity of this kind of measurements. And indeed, he told us that if we look at we should look at the squid geometry where we connect the two superconductors. Yeah, and obviously one of this left superconductor and right superconductor, they are connected to phonon buff. But what we are interested in is the phase-dependent heat coming between left and right superconductor. And if we calculate it, then and we put the left temperature of 500 millikelvin and buff 100 millikelvin, then actually the temperature on the right side is around 20, 30 millikelvin, which, as I understand, can be easily measured experimentally. So we were, yeah.
Before you go on, so can you distinguish between this helical Andreev and some highly transparent standard Andreev mode?
Yes, yes, that's what I'm saying. Is I can in the tunnel junction regime, because in the tunnel junction regime, this is Z equal 3.
No, tunnel. I mean, if you have a highly transparent Andreev level going down inside the gap, like
yeah.
close to pi, you would have also this kind of Andreev level, even for a
yes, so I would have it in a both situation. You are completely right, but that's why I'm tuning the barrier. But by tuning the barrier, I can distinguish them. If I do not tune a barrier, then both green curves, so this is the transparent, this is green curve, it's showing me similar behavior. Now, it might be that it's just some magnitude, but it will be difficult to distinguish. That's exactly the point. Yeah, that's why I'm using the barrier, because if I can change if I can remove the number of modes, if I have a gate on in my normal regime, which experimentalists can do easily at this time, then I can actually distinguish things. Make sense? Good. So, so this is actually one of the suggestions of the experiment. And, but obviously now with time, we ask ourselves, maybe there is even a better way of detecting the Majoranas. And this is the situation of the transverse system. So what happens is that we have now the gradient of the temperature. So this is again three-dimensional topological insulator. Yeah, and now here Josephson junction is in the transverse direction to the gradient of the temperature. And now one can, so actually in this particular calculations, because this is calculation still, we actually looked at the, we projected the full Hamiltonian into the lower Andreev bound state. And as you can see here, it's this 4-pi periodic spectrum, which is related now. Zy is magnetic field. So this is Zx, Y, and Z are magnetic fields in different directions. Z0 is the barrier again. And you can see that we just got some simple Andreev bound state spectrum. So if we now look at the thermal conductivity, it is quite robust. So again, I am looking at the thermal phase-dependent thermal conductivity. And what I can see is the k of phi as a function of phi. So in general, in y direction, the peak changes. So if I added magnetic field, I can change the peak, but the peak is quantized even for kBt of the 1/4 of the delta. Obviously, the shape a little changes. So what I am just drawing here, the thermal conductivity in the units of thermal conductance. Yeah? And obviously, you see the half quantized conductance. So now the question is this actually measurable? And we hope that it is. So this is the first experimental setup, which I at least saw in Würzburg by Lorenz Molenkamp. And they actually can look at the Josephson junction and make the perpendicular temperature gradient, as you can see here. So this is heater, this is detector, this is niobium, this is on mercury, 3D mercury telluride material. And they are about to measure something. So let's see what will happen. So this was actually to show you that the thermal transport can be quite useful for to use it to observe Majoranas. But now, as Alex already said, he is not so surprised, but I think many people were, that actually the spin-free half Hamiltonian can give me much bigger variety of the Majoranas than the usual electron gas. So let me just remind you something first. So these are the papers which we did with Amir Jacobi group some time ago. So the idea was to have an Rajba two-dimensional electron gas with Rajba spin-orbit interaction. And then if you put magnetic field in the right direction, here in the x direction, then you actually get the huge topological phase diagram, much bigger than you would expect for the wire or for the topological insulator and so on, because as you can see, this is a phase difference phi as a function of Zeeman energy, and Zeeman energy is in the units of Taulev energy. And you can see that there is a topological regime which is quite large. So it's not only for phi equal pi, but also in a much larger thing. So for the zero Zeeman energy, you get nothing. And the reason for this is that here you have a double degenerate state. So you have spin up and spin down. I mean, and the Rajba obviously splits it, but you have two species. So you are not spinless or spinful, how you prefer to call Kitaev model. And what happens is that here, with the increase of the magnetic field, so these are, as you can see here, they measured non-local conductance. And as a function of increasing of the magnetic field, you can actually see that the dip around the zero bias becomes a peak. Yeah? And obviously, it is not quantized because these two Majoranas overlap. And it is quite difficult. Obviously, one can do simulations, and one believes that there is some interesting signature, but we didn't claim this is Majorana. We just claim it that we can tune phase in the system and see something interesting. Good. So now let's do the same calculation for the Luttinger model with J equal 3/2. So this is now, so this is typical mercury telluride bulk. So this is actually the band structure, and this is actually the gallium arsenide. So what I am claiming is that I can use many different models as long as I use Luttinger model. So what is Luttinger model is really model for light hole and heavy hole, which are coupled. Yeah? So this is exactly the model which I am drawing here. So there is some quadratic term, obviously, because they have curvature, but there is also the coupling between a light hole and heavy hole. Yeah? And this could actually could describe any of these materials. So alpha tin mercury telluride, p-doped gallium arsenide, and even some kind of more interesting materials which are correlated, which have quadratic band touching. And now what I do is the same thing as I did before. So I just take the Josephson junction, I put a magnetic field in the direction of the supercurrent, and now I have this Luttinger model plus the superconductivity, obviously, in the parts here. Again, Josephson junction. And then I have a Zeeman term, which is acting in this direction. I again have to remove degeneracy in my system. And if I do this, then I don't actually, in 2D Luttinger model, I do not require Rashba or BIA term, so bulk inversion asymmetry term, to get the Majoranas. And so let me show you why. So one can actually look. So my student knew that I like matrix, so he did all of this in this kind of nice way here. So I mean, so you see topological phase diagram. So here is the phase, and here is magnetic field. And this black lines gives me the phase diagram. So -1 is determinant of the scattering matrix, and -1 means that I am in the topologically non-trivial regime, while +1 means that I am in topologically trivial regime. And we can indeed calculate the state of lowest energy in all of these regimes. And we actually see that indeed in the regime where I expect that I have non-trivial phase, I get the right topological invariant, and I also get the localized states, which are quite nicely localized here. Okay, so what does it mean? So how I call it actually emergence, intrinsic emergence of the Majorana fermions, because I don't need any extra Rashba or bulk inversion asymmetry term in the system. So why is it like this? So one can actually look up, and indeed in the Hamiltonian, there is a term which is px/py, but also commutator of the jx and jy, which gives me the term which is between light Hall and heavy Hall, which is similar to the spin-orbit interaction. So this is not so surprising that we could have some effects, but additionally to this term, we also need to have a gradient of the superconducting order parameter, and we can achieve it very easily. We can achieve it by the fact that we have superconducting or Josephson junction. So we obviously as well have a gradient over the superconducting order parameter. So indeed, what happens is that I don't need strain, Rashba, or BIA terms to get a topological phase. So this is like an intrinsic spin-orbit interaction which is in the system and which gives me non-zero Majoranas or non-zero topological phase. So let me summarize. So as I tried to convince you, there are different setups where maybe Majoranas are easier to find in the thermal transport than in the electrical transport. And we hope that the Majorana, at least theoretically, can be. So we can also show that for the p-doped gallium arsenide, if I take only Luttinger model, I also can get Majoranas much easier than for the electron situation. So I would like to acknowledge my collaborators, especially the PISA group with Francesco and Alessandro, and experimental group in Würzburg with Lawrence Molenkamp, who is trying to do these experiments. And then Uni Duisburg, when we started to do this thermal calculation with Björn Soffmann, he is now actually a professor over there. Thank you very much for your attention.